So now we're going to talk about compounding interest at faster rates than just annually. So our original equation that we spent a long time on, this helped us when interest was compounded every year. So remember, that means that you deposit $100 into the bank has 2% interest, you get a 102 back out, and then you go back and you deposit that 102, you get 2% of 102 back out at the end of each year. But some accounts allow you to basically add that money back in at faster rates, so you don't have to wait until the end of the year to add the money that you've earned back into your account. That means you're compounding it at a faster rate. So let's take a simple example here. We put $1,000 into a savings account that accrues 12% interest every year. Money after 1 year, that's going to be 1.12 times 1,000. So let's say instead we're compounding semi-annually instead of just annually. Then you're gonna, after half a year, you're gonna have $1,000 times 1.06 instead of 1.12 because you've used up half that interest that you've gained. You're adding that back in to your bank, and then you're getting interest on that money as well. So you do that 1.06 again. If you're doing it quarterly, then you have $1,000. Now you're going to break it into 4 different pieces, so you now only have 3% each time. But you're going to do this 4 times because it compounds 4 times over the course of the year. Monthly, that means it compounds 12 times over the course of the year. So you're going to have 1.01 to the 12. Daily, that would mean we're going to do, we got to break that 12% into 365 different pieces and then multiply that 365 times. So let's see, these numbers would actually come out to be 1120, 1123.6, 1125.51, 1126.8, and 1127.47. Okay, so I'm gonna now generalize this formula step by step. So if we wanted the amount after 1 year, we're gonna do our initial amount here, 1,000 times 1 plus 0.12, that's our interest rate, divided by the number of times that you want to compound that interest, all raised to the number of times that you want to compound that interest. So in the case of quarterly, n would be 4. In the case of semi-annually, n would be 2. In the case of monthly, n would be 12. Let's say instead we wanted to know what it's going to be after t years. We can do that by just adding a t to our exponent, so we multiply all of those extra years on top of just the first year. And then finally, let's say we want this to work for any problem. We're going to take out our 1,000, let that be a 0, your initial amount. We're going to take out 0.12, let that be r, whatever your interest rate is. And then we have this generalized formula. So this is formula number 3 that you'll need for word problems. This example, then you can pause the video and try this example on your own to figure out if you understand how to use this formula. Otherwise, you can watch me do it. I just want to make one note here. N is the number of periods you split a year into. Okay, so AT Cody has $450, puts in an account that accrues 24% annual interest. How much money will he have after 3 years? Okay, so let's just first set up an equation. So we want to use this formula. A0 is going to be 450 because that's what we start with. Our interest rate is 24%, so this is going to be a 0.24 divided by 12 because we're compounding monthly, so that means you're splitting the year into 12 parts. And then up here we have 12t. In this case, we are trying to figure out how much money he has after 3 years, so you're going to plug in 3 for 12 and then use your calculator to figure out what this is. We should get about $918. If we were putting it into account where it has 24% annual interest, but it was compounded quarterly, we would make those ends 4s instead of 12s, and we would just solve it out the same way. Okay, so there's one more type of problem, which is, let's say that you can continuously compound your interest now. So what does that really mean? That's basically if you split your year into tiny pieces. So instead of compounding daily, maybe you compound every single second, or maybe you compound every single millisecond. You're basically just constantly compounding it at all times. That's what continuously compounding means. And here I'm just going to give you the formula. I'll talk a little bit about where it comes from, but I'm first just going to give it to you. So this is what you'll do if you have continuously compounding interest instead of interest that compounds monthly or quarterly. The E in this case is a mathematical constant. E is like similar to pi in that it's always equal to 2.7182 and so forth. Similar to how pi is 3.1415. E is 2.7182, and it's just another one of these mathematical constants. Basically what E is if you start, what this expression will approach if you start plugging in really large numbers for n. So if we plug in 1 for n, we're going to get 2.5937. If we plug in 10,000 for n, we're going to get 2.718, 2.718. If you plug in 100,000, basically if you keep plugging in really large numbers, this is what this expression will become. It becomes E. And so when this is saying as we make our ends, as we split the year into bigger and smaller and smaller chunks, say we split the year into 100,000 chunks, then you're basically going to be approaching this mathematical constant E. If you don't get what I just said with this chart, that's okay. We're going to practice actually just employing this formula. We're going to skip this part. So this part, explaining this part, is much more difficult than actually applying the formula, which we're going to do in this example here. So Jennifer invests the sum of money in a retirement account with a fixed annual interest compounded continuously. So that's how you know that you're going to have to use this formula. So AT equals what her initial amount was. Or let's just start with our formula. We know we're going to have to use this one. So, okay, we know the interest rate is 6%, so we can fill that in for R. We know that we don't know the initial amount, so I'm going to leave that. We know that R is 0.06. We want to know what it is after 17 years, so we're going to use 17 here. And then we know that after 17 years it reaches this point, so we're going to plug that in for AT. And then we're going to use our calculators to solve for A0. So you'll figure out with this part, plug that into your calculator. There's a button, e to the x, that you can use. Ask Ms. Vasquez if you don't know where to find it on a graphing calculator. And you'll eventually find that A0 should be 3572. So again, A0 is always your initial amount. R is always your rate. T is always the time that passes. So we really have 4 key formulas. Your note sheet doesn't have this part, so just write it down somewhere else on your sheet. But the 4 key formulas, we have simple compounding interest. We have our half-life formula, or our doubling time formula, or our tripling time formula. We have our compounding interest formula. And then we have our continuously compounding interest formula. So if you see the words continuously compounding, you use this one. If you see the words half-life or doubles, or you see that something doubles, you're going to use this one. This one, if we compound monthly, quarterly, and this one's just a simple compounding. If you don't see that it's compounding monthly, quarterly, semi-annually, then you're going to use this first one. So on the word problems, you're first just trying to figure out which of these 4 are we going to use, and then you mostly just plug in the things where they belong. Last thing, if you have questions, if you're stuck on this, please don't stress out too much. I'll be back next week and we can really work through these things when I am back.